Hi, this is the second part of 6.2, finding the inverses of functions. And like we said before, functions are nothing, the inverse functions, to exist, they have to be one-to-one. So what I did was I wrote down what the definition of an inverse is. It says that f of x be a one-to-one function. G of x is the inverse of f of x provided for every ab that satisfies f of x. Then BA has to satisfy the G of x, which is the inverse. So simply put, I'm trying to just narrow it down as simple as I can. What an inverse is going to do is just switch the ordered pairs around. So if 2, 3 works for the function, then 3, 2 is guaranteed to work for its inverse. So if PQ works for the function, then QP is going to work for its inverse. So that's what they do. Okay? Now, the notation for the inverse, we don't call G of x the inverse of f of x. That gets kind of confusing. So we want to get, sometimes you're dealing with more than one inverse. So we want to keep the same lettering. So instead of calling it G of x, we'll call it f to the negative 1 of x. And you read that as f inverse of x. You don't say it f to the negative 1. You read it as f inverse or the inverse of f. Either way, that would do either one. But you don't call it f to the negative 1 of x. Although that's kind of what it looks like. So, but that's what inverse does. It just switches all the ordered pairs around. So that's going to make example 1 very simple for us to do. Example 1, I gave you a function by listing the ordered pairs, and I want to name the inverse. So like I just said, you switch all the ordered pairs, so it's very simple. So the f inverse is going to be the ordered pair of 3, 2, because that switches 2 and 3 around, 7, 5, because that switches 5, 7 around, negative 1, 9 around, and then negative 4, 8. So you don't change any signs on the numbers, you just change the order that they come in. Because if AB works for the function, then BA is going to work for its inverse. So now, prior to this section, we talked about 6.2 about one-to-oneness and why one-to-one is important. Look what would happen if a function is not one-to-one. So let's say 2, 3, 3, 5, and then 5, 3. Well, let's make it 7, 3. So we don't get confused there. So these are 3 ordered pairs. It's a function because there's every x coordinate is there one time, the 3, the 2, the 3, and the 7. But it's not a one-to-one function because there's a 3 that's repeated here on the y coordinate. So it's not one-to-one. But if you try to find the inverse based on that, based on that function, it would look like this: 3, 2, 5, 3, and 3, 7. Do you see a problem with this? If you said there's a repeated 3 there, that means it's not a function, you'd be correct. That was why we talked about one-to-oneness first, because all functions, not all of them, is going to have an inverse. It's only the ones that are one-to-one. So that's what the inverse functions are. Now, the reason we talk about inverse functions comes a little later. So you're going to stay tuned on that one. That takes a little while to explain why we even talk about this subject. There is a reason. It's not just because we're just teaching you concepts. There is a reason for that. That comes a little bit later when we hit the exponential functions and the logarithmic functions. So it's a little bit else later to talk about that one. And but anyway, so this is not an inverse. So this does not exist. So it's only the one-to-one functions that have inverses. Now, on this example 2, I am going to show you that these two functions are inverses of each other. And like we talked about in class, okay, this is just a reminder, so you should be in class to see this anyway. I want to show you that these two functions are inverses. F composed G of x must be equal to what? Do you remember what we talked about in class? It has to equal x. And then G composed F of x must also be equal to x. It's called the theorem of inverses. So F composed G of x. So this one's going to be F of G of x. Now, we did compositions back in 6.1, so that should be familiar to us. G of x is going to be 1/2 x minus 3. So there's a reason why we order things the way we order them, because you got to talk about compositions before you can talk about this stuff. So plug 1/2 x minus 3, or substitute 1/2 x minus 3 back into the f function. So the f function says 2 times input plus 6. So it's going to be 2 times 1/2 x minus 3 plus 6. And if all goes well, and if these are actually inverses, this must be x. So 2 times 1/2 of x is x. 2 times -3 is a -6, plus 6, well, look at that, it is x. So far, so good. Okay, so f composed g of x is x, but the other one must be equal to x as well. And it is. Let's prove it. So g of f of x, so that's going to be g of f of x, which is 2x plus 6. That's what f of x is. And so g of x is 1/2 input minus 3. Well, what is input this time? Well, the input this time is 2x plus 6. So it's going to be 1/2 of 2x plus 6 minus 3. If all's well, this should be x as well. So 1/2 of x, 2x is x. 1/2 of 6 is 3. And bring that minus 3 down. Look at that, it's x. And like we talked about in class, why does this have, what's happening here is if two functions are going to be inverses, if you take something and you plug it into one function and you get an output. And in that output, you plug it into the other function and it's got to go back to the same as what you started with. If you look at this problem, I started with an x, I ended with an x. I started with an x, I ended with an x. So it's got to be a circle is what is going on. So it goes x to something else, and then put the something else back in, and it goes back to x. So the something else is about right here. So when you put this in here, so it goes in right there. That's the something else. Then you got to go back into, and it goes back to x. Now, I'm not a big fan of example to tell you the truth, because most of the time you don't have the inverse. You are actually going to try to find the inverse. So this one, the book is letting you know that these are inverses. So you know they are to begin with. So there's a difference between show and find. Example 3, we're going to find the inverse. Example 2, we're going to show their inverses. There's a big difference in the amount of work there. Okay, showing is just using a theorem to prove that two things are actually inverses by that theorem. You're not finding anything. They tell you that these are inverses to start out with. They just want you to verify or show that they are. Now, example 3, you're given the function, and you don't know the inverse yet. You have to find it. And like we talked about in class, it's like a 4-step process. And if you recall, the first step is to change f of x to y. Then you interchange the x's and the y's. Then you solve for y in that second step. And then that third step is a doozy sometimes. In this case, it will be a doozy. And then the fourth step is to rewrite y back to f inverse. So let's do that. Now again, those steps I just counted with my fingers is in your notes. So you need to be coming to class. So find the inverse of f of x equals 2x plus 3 over x minus 5. So y equals 2x plus 3 over x minus 5. That's your first step of your 4. Second step is to change y to an x and change x to a y. So it's x equals 2y plus 3. And if you want to know something that's funny here, this one right here is actually the inverse. Well, can I stop? No, you can't stop because you got to get in the right notation. So x equals 2y plus 3 over y minus 5. I have to solve for y. So if you multiply the y minus 5 to the other side, you get x times y minus 5 equals 2y plus 3. So the goal here is to get to y by itself. And this is why I said a while ago it's a doozy sometimes, because there are y's on both sides. So we have xy minus 5x equals 2y plus 3. Now we got to solve for y, but there's one here and there's one there. So we need to isolate the y's on one side and everything else to the other side. So the 2y is going to come over here. So it's going to be xy minus 2y. And this 5x, this negative 5x, does not have a y, so it's going to go to the other side. So it's 5x plus 3. And then we're going to factor the y out. And that's the doozy part right there. What I just did was, when I said it's a doozy sometimes, I put that down like as if that was the most natural thing to do. But most people don't know what to do with that because they cannot combine the xy and the minus 2y. Okay? But that's what you have to do, because there's two y's and you have to solve for them. There's two of them. You can't put these two terms together because they're not like terms. You learned that in Math 101. You can't put those together. So if you want to turn two y's into two terms into one, then you got to take it out. You got to factor it out. So there's a y here and there's a y there, and factor that y out. So that's one of the reasons you learned how to factor back in the day. So to do stuff like this. Then you got to divide by the x minus 2 to the other side. So you get y equals 5x plus 3 over x minus 2. Okay? So then the last step is to change y back to alpha inverse. And that should be the inverse right there, unless I made a mistake. I don't think I did. But that should be the inverse of the original function. Now, we're good. We're done. Now, sometimes on a test, I'm always kind of like, okay, did I make a mistake? Do I need to go back and recheck my work? And I always wish that there was a way I could do it to make myself at least feel good that I think I did it right. And this is one of those kind of problems that you can do that. What you do is you put an ordered pair in the original function, and knowing what a definition of an inverse function is, that number reversed should work for the other one. Now, it doesn't prove it, they're inverses, but it sure does make you feel better. So if you put, let's say, a point in this one, let's put 6 in. You're going to see why I put 6 in there in a second. Put 6 in here. 2 times 6 is 12, plus 3 is 15 on top. And then 6 minus 5 is 1. So it's going to be 15 over 1, which is 15. Can you figure out why I chose 6? Of all the numbers there were, I chose 6. Why do you think I chose 6? If you said because that makes the denominator 1, you will be correct. So that's 6 comma 15. So if these are truly inverses, then 15, 6 should work for that one. And if it doesn't, then I know I made a boo-boo somewhere along the way there. So let's put 15 in and see what happens. 5 times 15 is 75. 75 plus 3 is 78. And then 15 minus 2 is 13. And I believe if you divide 78 by 13, I believe pretty sure you get 6. And so it does actually switch that order pair around. And that's what inverses are supposed to do. And a lot of people don't appreciate the beauty of that. I mean, because what you're doing is you're creating a function that will undo everything that another function will do. So it's kind of like getting a copier machine. And I mean, getting a copier machine and running a copy through there and making something else on the other side, and then taking that copy and jamming it back into it and go back to the original. So that's really what you're trying to do. So that's what these inverse functions actually, that's the purpose of them. So, but anyway, that is the conclusion of 6.2.